screen visible to you all?
Yes, ma'am.
Okay. So see, this question says that a cube has been placed on the x-axis. So separation of this cube from the origin, this is A, and the length of this side, or the side basically of the cube, is also A. Electric field is given to you as alpha x to the power half. And it says electric field exists along x-axis. So electric field, this is in this direction, along x-axis. So along x-axis means positive I cap. Then it says you have to calculate the flux through the cube and also the charge enclosed. So see, as I've told you, for the first thing, whenever we calculate electric flux, we have to check the area vector. So see, let's check all the faces of the cube. If I talk about this front face, this face which is in the interior, this front face, area vector is directed outwards in this manner. If you drop a perpendicular, it will be outwards. Electric field is directed along the x-axis. So what is the angle between area vector and electric field?
90 degree.
90 degree. So whenever you have cos as 90 degree, cos 90 is 0. So means because of this surface, you do not get any flux. Flux because of the front surface is 0. Then what about the back surface? The surface which is behind this back surface. See, if you drop a perpendicular, that will be outwards, again in front of it. Electric field is again towards the x-axis. So the net angle is again 90 degree. Means because of the back surface also, we won't be giving any flux. Now see, what about the top surface? See, if I drop the area vector in this manner, this will be the area vector for this top surface. Again, electric field is directed towards the x-axis, whereas the area vector is directed towards the y-axis. So again, it is making an angle of 90 degree. It means no flux will be contributed by the top surface. What about the bottom surface? See, if I drop this n cap, means the area vector. If you look at the electric field, this is directed towards the x-axis. Now the area vector is directed towards the negative y-axis. Again, both are making an angle of 90 degree. So it means because of all these four faces, no flux will be contributed. But what about this right-hand side face? If I talk about this right-hand side face, so if I drop the area vector, this will be it, means the perpendicular to the surface. Now it is not making an angle of 90 degree. So it means flux will be contributed by this surface. Same is the case with the left surface. If I drop a perpendicular on this surface, n cap. If I drop a perpendicular on this surface, then n cap and electric field both are directed in, and both are anti-parallel, means directed in 180 degrees. So here also flux will be given by left. So if you have a cube, electric field is given to you. For each phase, you have to check whether every phase is contributing to the flux or not. So in this case, we have seen only right-hand side phase and the left-hand side phase is contributing to the flux. Now see, the magnitude of electric field is not given to us. Electric field is given in variable terms. Electric field is alpha x to the power half. So x is the distance from origin. So let us one by one calculate it for the right-hand side phase, then for the left-hand side phase. If we add both of these flux for the left and right, we get the net flux through the cube. So see, the formula of flux is what? E S cos theta, or E dot S, this is flux. So for the calculation of flux for the right-hand side, see, electric field for the right-hand side will be what? The general electric field is alpha x to the power half. Now see the separation of the right-hand side face from the origin. Cube is separated from the origin by distance A. The side of the cube is A. So by how much distance is this right-hand side face separated from the origin?
2a.
A plus A.
A plus A, that is 2a, correct. So instead of writing x, now I'll be writing 2x. So alpha will be the constant, so I cannot change alpha. Instead of writing x to the power half, now I can write 2a to the power half. And what is the direction of electric field? It has given to us towards the positive x-axis, means I cap. This is the direction of electric field. So I can write it in this manner: alpha root 2 a to the power half I cap. This is the electric field. Then the surface area for the right hand side face. For a cube, all the surfaces are plane squares. All 6 squares make up a cube. So if the side of this cube is A, so what will be the surface area of this right hand side face? A is this. All the sides are having dimension A.
A square.
A square. It will be A square. And see, what will be the direction of this surface area? Area vector is giving you the direction, and area vector is directed towards the x-axis. It means again it will be I cap. So if you calculate, surface area will be A square I cap. Now you have surface area with you, you have electric fields value with you. So phi r will be what? And cos theta, theta will be 0 degrees, because both are pointing towards the x-axis, means 0 degree, making an angle of 0 degree between them. So cos 0 is 1, so we will simply write alpha root 2 a to the power half multiplied by alpha root 2 a to the power half I cap. Both of these will be I cap. Now see, I cap dot I cap is what? I cap dot I cap is 1. So if you multiply both of them, you will get alpha root 2a, no, a square will be here. Just a second. This part, electric field I've already written. So electric field is this. Surface area is only a square I cap. This is the surface area. See, electric field dot surface area, and cos theta is 0, so cos 0 is 1. So see, alpha root 2 a multiplied a to the power half multiplied by a square, this gives a to the power 3 by 2. This is I cap dot I cap is 1 already. So this is flux because of the right hand side that we get. Now see, this is not our final answer. Why? Because flux will also be contributed by the left hand side. So now tell me, what will be the value of x for left hand side?
A.
Yes, A. It will be only A. You have to check the separation of the cube or whatever face you are talking. Whatever face you are considering, the separation of that face from the origin. So this left-hand side face is only separated by this distance, which is A. So now instead of writing 2A, the electric field for the left-hand side face. For the left face, this will be electric field for the left face and multiplied by the surface area for the left face. Now see, flux
Ma'am,
for
how
the...
is A 3 by 2, ma'am? I mean the power of A.
Where?
Ma'am, A root, I mean alpha root 2 A 3 by 2. A power 3 by 2.
So what should be the answer? What are you saying? It should be 2A.
No,
Yes,
ma'am.
Krishna?
No, ma'am. In the power down below, ma'am. When you're calculating the
Okay, it would be 5
5
by
by
2, no?
2.
Yes, it would be 5. This will be 5. This will be 5 by 2. Now see, electric field for the left hand side. So see, this will be electric field for the left hand side multiplied by the surface area. So see, surface area will be A square only. It's just that now instead of writing A square, we'll be considering the direction of area vector. Now the area vector is pointing towards the right hand side, towards the left hand side now. So see, surface area for the left hand side, this is. See, this is pointing now towards the negative x-axis. So it means it will be minus of I cap. So A square minus I cap you have. This is the difference. So now you are not required to take the angle even because you have considered the negative sign with you. Electric field for the left hand side. This is alpha. It was x to the power half. So it will be A to the power half only. This will be alpha a to the power half. Now the direction of electric field. Electric field's direction is not getting changed because electric field is remaining the same. Electric field is directed towards the x-axis, positive x-axis. So positive x-axis has which unit vector?
I cap.
I cap. So again electric field will be I cap only. So electric field will be a alpha alpha e to the power half I cap. Now see, if you take the product for the left hand side, it will be alpha a to the power half I cap dot a square minus I cap we'll be considering. So this will be a square minus I cap. So again it will be similar to the previous one. It's just that we are not getting root 2, we are getting this and minus sign extra. So minus alpha a to the power 5 by 2. This is flux because of the left hand side phase. So now see, you have the flux for right hand side phase, you have the flux for left hand side phase, and flux because of rest of the 4 phases is 0. So net flux will be what? Net flux will be simply the sum of the flux of all the phases. So because of rest of the phases flux is 0, let us only write flux because of the right hand side phase and flux because of the left hand side phase. So see, flux because of the right hand side we got as alpha root 2 a to the power 5 by 2, and this is minus alpha a to the power 5. So see, a to the power 5 by 2 and alpha, this can be taken common. What will be left? Root 2 minus 1 can be left. So see, root 2 is what? 1.4. You can subtract 1, that will be approximately 0.4. So you can write it as 0.4 alpha a to the power 5 by 2. This is your flux that you get. But this is the answer of the first part only. Let's see the second part of the question. The question has not ended over here. The question has asked you to calculate the charge enclosed. So you know the flux. If you know the flux, then you can easily calculate the charge enclosed. See, according to Gauss theorem, which we did in the last class, phi is what? Flux is Q charge enclosed divided by epsilon naught. So what is charge enclosed? Charge enclosed is flux multiplied by epsilon naught. Epsilon naught is a constant which you know. Flux we have already calculated. So can we get charge enclosed by just multiplying 0.4 alpha a to the power 5 by 2 with epsilon naught?
Yes.
So this will be your final charge. Is this clear now?
Yes, ma'am.
Yes.
Just note down this question as well as its solution. Written?
Yes, ma'am.
All of you? Okay, so we had done a very bit revision of the last class. Gauss theorem is left. So yes, Hiba, you tell me, were you there in the last class? What is meant by Gauss law? Or what is the statement of Gauss law? Kulsum, you were absent in the previous class, no?
Yes, ma'am.
So yes, can any one of you tell me what was Gauss theorem?
Electric flux through a closed surface is 1 by epsilon naught times the total charge enclosed by the surface.
Enclosed by the surface, no? Whatever is the total charge that is enclosed within the surface. So yes, this was Gauss theorem. Gauss theorem says that whatever is the net flux through a surface, this is 1 by epsilon naught times through the to the charge enclosed. Now see, let's begin with the next topic, that is continuous charge distribution. Gauss theorem, electric flux, this is over. If we get time, we'll do more questions on it then. Now see, the next topic that you have is continuous charge distribution. What is meant by continuous charge distribution? So see, there are three kinds of charge distribution. Charge distribution is what? The way charge is distributed over a surface. So majorly you have three kinds of charge distributions. First one is your linear charge distribution. Linear charge distribution. So see, in case of linear charge distribution, if I take a wire with me and there are positive charges present on this wire, all right, there are positive charges present on this wire. If I tell you that L is the length of this wire, total length of this wire is capital L, and the total charge is capital Q. So what is charge Q? Charge Q is the charge distributed uniformly on this wire. Charge uniformly distributed. So if you have a wire with you of length L, the whole charge is uniformly distributed on it. And L is what? L is the length of the wire. L is the length of the wire. Now see, if I want to calculate what is unit length in this, what is the charge present on unit length? For L length, I know that the charge is Q. For L length, the total charge is capital Q. L length is what? L length is the whole length of the wire. Charge is the total charge on this wire. So if I ask you what is the charge present on a single unit length, how will you calculate?
Q by L.
Q by L. It will be Q by L. For L length of wire, you have Q charge. So for a single wire, single unit, what do you have? You will be using simple unitary method. Unitary method includes what? Charge divided by length. So this quantity that we are getting, charge per unit length of the wire. Charge per unit length means what? If I drop a very small section, unit length of the wire, whatever will be the charge enclosed on this. Let's say delta Q is the charge that will be coming on this part. So this quantity is known as linear charge density. This is known as linear charge density, which is represented through the symbol lambda. This is your linear charge density. So linear charge density means charge per unit length. Charge per unit length is linear charge density. So lambda will be what? Whatever is the charge per unit length. This is valid if the charge is distributed uniformly for uniform distribution. So what will be the SI unit of
Coulomb per meter.
coulomb?
Coulomb per meter.
Coulomb per meter.
Coulomb per meter, correct. So for charge it is coulomb, so it will be coulomb per meter. Charge SI unit is coulomb and length is meter. So SI unit will be coulomb per meter. Now see, just in case if you have non-uniformly distributed charge, if it is uniformly distributed, you can calculate using this formula. If it is non-uniformly distributed, then you can take a very small segment in the wire, very small part, let's say DL. So lambda will be given by differentiation, dq over dl. So when you will use dq over dl when you have non-uniform distribution. Non-uniform distribution. So if you have uniform distribution, then you can simply use lambda is equal to q by l. And if you have non-uniform distribution, you can use the differentiation, basic differentiation that you have already studied, dq divided by l. So do one thing. Firstly, note these points, then we'll do question on this. Atif, your first part is correct, but there's some error in your second part. Answer to the second part is not right. First part is correct. Okay, let's discuss it only. Charge of 10 coulomb is given. Yes, Krishna. Krishna, both answers are correct. Again, Atifa, first part is correct. Answer to the second part is incorrect. Just check it once again. Answer for the second part. See, charge of 10 coulomb is uniformly distributed on a wire of length 5 meter. So charge you have as 10 coulomb. Length of the wire you have as 5 meters. Linear charge density. We have just studied the formula of linear charge density is Q divided by L. Q is 10, L is 5. So this becomes 2 coulomb per meter. So linear charge density will be 2 coulomb per meter. This is answer for the first part. Now see, it says you have to calculate charge on 2 meter length of wire. What is 2 coulomb per meter? This is charge present on unit length of wire. Charge on 1 meter of wire. Linear charge density is what? Charge per unit length means charge present in 1 meter of wire. So if the charge present on 1 meter of wire is 2 coulomb, 1 meter has 2 coulombs. So 2 meter will have how many coulombs? Simple unitary method. 4 coulombs. No. For 1 meter, you have 2 coulombs. This statement, this answer that we are getting, this basically means 1 meter of wire has 2 coulombs. When you're writing this, this means 1 meter of wire has 2 coulombs. So if 1 meter of wire has 2 coulombs, what will be the charge present on 2 meter of wires? It will be double of it. Or you can simply write it in this manner. Q will be what? Q prime, or let's say delta Q that you have to calculate. It will be lambda into L. Lambda is what? 2 length of the wire that is now given. Delta L, let's say delta L. This is now also 2 given, 2 meters. So this will be simply 4 meters. Or you can simply do this using your unitary method. That if the charge present on 1 meter is 2 coulomb, then charge present on 2 meters will be 4 coulomb. This was the case when the charge distribution was uniform. Let's do one question. If your non-uniform charge distribution is given. If I say linear charge density of the wire, let's say lambda is 2x. This is given to you as 2x, and you have to calculate the charge present on, let's say 10 meters. Calculate the charge on 10 meters length of wire. Now see the charge distribution that is given to you, lambda, the linear charge density, means the charge which is present on a unit length. This is non-uniform. Why? If you change the value of x, your charge per unit length will also get changed. If I say x is equal to 1, then charge per unit length means this lambda, linear charge density, this will be 2. If I say x is 2, this will be 4. So as I'll keep on changing the values of x, I'll be getting different values of lambda. So this shows that this is non-uniform. So it means we have to consider dq over dl. So see, dl, we can calculate lambda, we have it. We have to find the charge. So dq will be what? Lambda dl. All right, this will be lambda dl. So it is given in terms of x. So let's write it also in terms of x. dq will be what? Lambda dx, where x is the total length of the wire, because lambda is given in terms of x. All right. Now see, you have a very small part of the wire. You wish to calculate the charge on the whole, means on 10 meters. You want to expand it. So what you'll do? You'll simply integrate it. You'll do basic integration. Lambda is given what? Lambda is 2x. So dq, this will be 2x dx, and integration. Now see, from where do I have to integrate? From 0 to 10 meters. Why? Because the length of the wire, now that we have to calculate, this is given as 10 meters. So the limits will be from 0 to 10 meters. Now simple your integration. Integral of dq will give you q only, means the charge that you have to calculate. 2 is constant. See, whenever, all those who have forgotten it, if you have x to the power n, then while integrating, this becomes n plus 1 and it gets divided by n plus 1. This is how we solve it. So here x has the power 1. 1 plus 1 will be what? Now here in this case you have x to the power 1. So it will be plus 1 over here and 1 plus 1 over here. So x to the power 1 plus 1 is what? It is x to the power 2 divided by 1 plus 1, that is 2. This is how you use integration. If anybody is having doubts in solving or your basic calculus, you can ask me right now. And limits are from 0 to 10. So 2 will get cancelled. Upper limit square minus lower limit square. Why are we squaring it? Because x has the power 2. So this will be 10 to the power 2 minus 0 to the power 2. 0 is 0, so your charge will be 100 coulombs. Clear? Both the cases, non-uniform and uniform.
Yes, it.
All right. So note down this one as well. So this was linear charge distribution. Linear charge distribution, you have charge distributed on the length of the wire. Now see, if I talk about surface charge distribution. So instead of the single wire, which I was considering where the charge was separated, distributed, if I take a surface, a plane surface with me, this has charges present on it. Let's say S is the surface area of this plane surface, and again Q is the total charge distributed. This is the charge distributed. So what will be meant by surface charge distribution? This is same as linear charge distribution. It's just now this is 2D. That was one dimension only. Now you have two dimensions with you. It is a plane surface. So you here have surface charge density. Surface charge density. Surface charge density means charge per unit area. So linear charge density was what? Linear charge density was charge per unit length. Surface charge density is charge per unit area. So now you'll be having all the things which were regarding the length. Now you'll be having in terms of the area. So surface charge density, this is represented through this symbol, sigma. This will be charge per unit surface area. So if S is the surface area, take it as S, or A is the surface area, take it as A. So this will be again valid for uniform. Similarly, okay, now what about the SI unit now? Will it be coulomb meter again?
Coulomb per meter square.
Coulomb per meter square.
This will be coulomb per meter square. And again, if you have it for non-uniform, this was for uniform. If you have it for non-uniform, then sigma will be dq divided by ds. Similar for the linear charge distribution, the way you have studied it for linear charge. This is for uniform. So this is surface charge density, sigma. Lambda was linear charge density. Now, if I give you a question based on this, a very simple question, direct formula based. So let's say charge of 10 coulomb. It is uniformly distributed. Uniformly distributed on the surface area. Let's take the figure that you have as square. Surface area on the square. Or let's take sphere. Surface area of a, let's say we have it as sphere. Let's take sphere. So the radius of sphere will be given to you. Radius, let's say 2 meters. So you have to calculate the surface charge density. And you have to calculate charge on 2 meter square area. Now see, so in case of sphere, why I have given you sphere? Because in sphere, two cases can occur. One is if the charge is present inside. Other one is when the charge is residing outside. So this is the case when the charges are residing outside the sphere, means present on the surface area of it. So simply, charge is what? Charge is 10 coulombs. Surface area is given to you. No, surface area is not given to you. Radius is given to you. So we can calculate the surface area for a sphere. Surface area for a sphere is 4 pi r square. So this will be 4 pi R is what? Radius is 2 meters. This will be 2 square, which is 16 pi meter square. So surface area is 16 pi meter square, charge is 10 coulomb. What will be sigma? Sigma is simply Q divided by the surface area, surface charge density. So Q is 10, this surface area is 16 pi. So this is your final answer, or you can solve it further. This will be, you can subtract, you can divide both of these. So this will be 5, this will be 4, this will be 8 pi. And then the unit, this will be coulomb per meter square. This will be your surface charge density. Now say charge on 2 meter square. This means what? 1 meter square has how much? 5 by 8 pi coulomb of charges. So how much will 2 meter square be having? You can double it, or you can write in this manner that sigma is what? Delta Q by delta S. So delta Q will be what? Delta Q will be sigma multiplied by delta S. So delta Q we have to calculate. Sigma we have already calculated. Delta S we are given. So this is 5 by 8 pi. What is delta S? Delta S is given to you, means the surface area, 2 meter square. So this is 2 meter square. This will be 5 divided by 4 pi coulombs. Or you can simply use your unitary method and solve that. For 1 meter square, if it is 5 by 8 pi. So for 2 meter square, what will be the charge? You can double it. So 5 by 8 pi, you will be multiplying it by 2 again. So you'll get 5 by 4 pi. So this was surface charge density. Is this clear?
Yes, ma'am.
Just note down this, and one more charge density is left, that is volume. see the last type of continuous charge distribution that is left is volume charge distribution. Volume charge distribution. So if I have a sphere with me and the charge is present inside the sphere, means in the volume of it. So this is three-dimensional. Linear charge density was one-dimensional. Surface charge density 2. Volume charge 3-dimensional. So let's say V is the volume of the body. Q is again the total charge. So volume charge density, this will be charge per unit volume. This will be charge per unit volume. So this is represented through the symbol rho. Rho will be equal to charge means Q per unit volume, that is V. Now what will be the SI unit?
Coulomb per meter cube.
Coulomb per meter cube. This will be coulomb per meter cube. So again, this is valid for uniform, and if you have non-uniform, then rho will be dQ over dV. This will be for non-uniform. So all of you note down this. I am giving you a question. Now you all will answer. First note down this. Note down this and I'll give you a question. All of you should submit your answers. Yes, answers. So Atif and Krishna are correct. Fatima, sign I think you have taken wrongly. Just check up the sign that you have put. Otherwise, your magnitude is correct for the first part.
Teacher, it's not minus. It's showing that that is the answer.
Okay, okay.
Dash.
Then it's correct. Then it's correct. So calculate the second part also, Fatima. First part is right. See, what is the charge that you have? Yes, Kulsum, what is the charge that you have? Yes, Kulsum. Read the question. Charge is given to you.
10 coulomb.
10 coulomb. Charge is Q is given as 10 coulomb. And volume of the sphere. See, volume of the sphere is given by 4 by 3 pi r cube. R radius is given as 3 meters. Radius is given as 3 meters. Hamza, you can leave the answer in terms of pi. No need to calculate it. You don't need to divide it. Just give the answer in terms of pi only. Radius is 3 meters. So see, this will be 4 by 3 pi 3 to the power q. So 1 3 will get cancelled. This will be 9 into 4 pi, that is 36 pi. So see, what is the formula? Heba, what is the formula for calculation of volume charge density? Rho.
Q by V.
Q by V, correct. This is Q by V. So Q is given as 10 coulombs, V is given as 36. So this will be 5 by 18 by coulomb per meter. Now see, then it has asked you to calculate the charge on 3 meter cube volume of sphere. So see, this was the first part, this was the second part. So this means what? 1 meter cube has 5 by 18 pi coulomb of charge present. So how much charge will be present on 3 meter cube? Simply multiply it. So delta Q will be given by 5 by 18 pi into 3. This will be 5 by 6 pi. All right. So all those who did not try, just note down the solution. Done? See, before we move on to the next part, you have to know what is meant by Gaussian surface. So we have already discussed what was Gauss law. Gauss law said that phi is 1 over epsilon naught times the charge enclosed, means q by epsilon naught. This was Gauss law. Gaussian surface is just geometrical surface used to enclose the charge that we have. For example, just there are two conditions for a surface to be considered as a Gaussian surface. The first condition says that it has to be a closed surface. The other condition says that electric field should be parallel or perpendicular to the surface, parallel or perpendicular to the surface. So see, if I give you a wire with charge distribution, if this is the wire that is given to you with the charge distributed in this manner. So if I draw a cylinder, these charges are not enclosed. If I draw a cylinder, now just look at the cylinder. Cylinder is a closed surface. So see, this will be now the Gaussian surface. An imaginary surface that is drawn to enclose the charge. This will be the Gaussian surface. So for a linear charge distribution, the Gaussian surface is cylinder. This is cylinder. Cylinder for linear charge distribution. Why? Now the charge has been enclosed. Or if you have a sphere and the charges are outside this sphere, then you can draw a sphere. Now within this will be the Gaussian surface now. This will be the Gaussian surface. So for a spherical charge distribution, the surface that you say or the Gaussian surface that you choose is a sphere. So we need Gaussian surfaces for the calculation of few things. For example, if you have to calculate electric field due to infinitely long wire, firstly understand what is meant by infinitely. Let us calculate electric field due to infinitely line wire, you can say, or you can say long wire even. So infinitely line wire, or you can also call it long wire. Now again, if I have a line charge with me, so what is the Gaussian surface that we choose for a line charge? Cylinder. So if I say this is the line charge that I have and charges are present on this, so I have to draw a cylindrical surface. Now this will be the Gaussian surface. Now the charges are enclosed. And let's say the radius of it or the separation, this is smaller. Now, whenever we are considering cylinder has three surfaces. This is the first surface, this is the second surface, this is the third surface. So flux through the first surface. Electric field, let's say electric field is directed upwards. This is the direction of electric field. E is the electric field, R is the radius of the cylinder. So can you tell me, if this is your first surface, this is your first surface, then tell me what is the angle between the electric field and the area vector?
0.
0. Correct. What if I change the direction of electric field? Now tell me. If I say this is the direction of electric field, now what will be the angle between area vector of first surface and electric field?
90 degree.
90 degree. Why? See, n cap will be over here. Electric field is directed towards the positive x-axis. So electric field and area vector are making an angle of 90 degree. So let's say electric field is directed in this direction. The electric field is directed towards the right hand side. And let us also take some length of the cylinder. Let's say L is the length of the cylinder. What about the third surface? Where will the area vector go? If this is your third surface, downwards, correct. So this will be downwards, and electric field is directed at this
90 degree will be the
90
angle.
degree. 90 degree will be the angle again. What about this surface? This curved surface only, this surface. If I take a small section, let's say I have taken this section, area vector will be here. So now what will be the angle?
0 degree.
0 degrees. So see, cos 90 degree, if I'll calculate phi1 will be E S1 cos 90, which will be what? This will be 0. Similarly, for the third phase, this will be E S3 cos 90, that will again be 0. So flux will be contributed by which surface? Only the second part. So flux for the second surface will be the total flux. So how do we calculate the flux? This will be E S2 cos 0 degrees, which is electric field multiplied by S2. All right, now what is the surface area of a cylinder? Curved surface area of a cylinder, this is given by 2 pi RL, where L is the length of the, let me write it down. L is the length of the cylinder, R is the radius. This is the basic formula, you all know. L is the length of the cylinder. So you have the surface area with you, you have the electric field with you. So can I write phi 2 equal to E 2 pi RL? Is this correct? Is this fine?
Yes, teacher.
All right. Now see, now if I apply Gauss law says what? Flux in this surface only, flux is also, this is the total flux. This is phi that we have, net flux. Gauss law also says that phi is total charge enclosed per unit by epsilon naught. This was the Gauss theorem that we have seen, Q by epsilon naught. So this says, Gauss law says that this is charge enclosed per unit epsilon naught. Now see, we have just studied for a single wire, what is the charge distribution that we take?
Q by L.
Yes, Krishna?
Q by L.
Q by L. So see, linear charge density that we had studied, lambda, this is what? Q by L. So Q is lambda L. Now I have the value of charge with me. So if I put it in this, phi will be what? Phi will be, instead of Q, I will have lambda L divided by epsilon naught. So you have two flux values with you. One value is what? One value is this, 2 pi RL. Other value is what? Other value is lambda L by epsilon naught. So both of these fluxes are equal. So can I equate them?
Yes.
So E 2 pi RL will be equal to lambda L divided by epsilon naught. Length will get cancelled. Electric field will be equal to what? This will be lambda. Everything will get divided, means 2 pi epsilon naught. This will be the value of electric field for a single wire if you have linear charge density. All right. So electric field is inversely proportional to the radius. If you are able to observe, for a point charge, what did we have? For a point charge, we had E is equal to KQ divided by R square. E was inversely proportional to R square. For dipole, you had Kp divided by R cube mainly, where E was inversely proportional to R cube. Now for linear wire, you have E is inversely proportional to 1 by R. So if you plot the graph, this is electric field, this is the separation, it will be in this manner. Clear to all of you?
Yes, ma'am.
All right. So just note down this as well. Is it clear to the rest of you? Hamza Shekhani, Fatima Munir, Kulsum, Akifa?
Yes, ma'am.
Done? Yes, class, are you all done?
Yes, ma'am.
Yes, teacher.
All right, okay. So I'll leave you early today. I'm stopping here today. In the next class, we have 2 cases left. Electric field for calculation of plane surface and calculation of electric field for spherical space. All right. So we'll continue in the next class. This is what. Okay. Bye-bye.
Thank you, teacher. Have a
Thank
nice
you,
day.
ma'am.
Thank you, teacher.